Hi students, welcome to the new session of our refrigeration and air conditioning third module. So today we will deal with refrigerants. So students, refrigerants. So what is refrigerant? So students, you know there is a working fluid. So you have a vapor compression system, right? So this is a condenser, this is a compressor. So this is evaporator, this is compressor, this is condenser, right? And this is expansion valve. So you know that a working fluid, there is a working fluid which is flowing through this cycle, so through these members, right? So a working fluid will absorb heat from the space to be refrigerated and carries this heat through compressor where it is compressed to a higher temperature and higher pressure, and it reaches condenser, and this working fluid rejects heat to the ambient space, right? Ambient space. And this is Q1, this is Q2, and this condenser will so this refrigerant will get condensed to liquid form, and the pressure may remain at that same pressure remains at that same value, and it moves to the expansion valve where its pressure is getting reduced, and then cycle continues. So this working fluid which absorbs heat from the space to be refrigerated, and which which rejects heat to the atmosphere is called what? Refrigerant. So refrigerant is that particular working fluid. So a refrigerant is the fluid for heat transfer in a refrigerating system that absorbs heat during evaporation from the region of low temperature and pressure, and releases heat during condensation to a region of higher temperature and pressure. Okay, so refrigerant is that fluid or working fluid. So students, in our first reference, even before the introduction, in the initial stages of introduction, initial periods of refrigerations, our refrigerants were natural ice. So I have already told you during the introductory part, natural ice and a mixture of ice and salt, these were the refrigerants used in the initial periods of refrigerating systems. Initial period where cooling was required, and then either ammonia, sulfur dioxide, all this and carbon dioxide, all these compounds were used as refrigerants in compression cycle refrigerating system. So these refrigerants are not used in compression systems, right? They are just used for cooling directly through heat exchangers. This through direct contact, it absorbs heat, right? So these are not used in machines or vapor compression systems. So, but these gases slowly started to be used in our compression cycle refrigeration machines. Okay, so most of the early refrigerant materials have been discarded now. So these most of the means most of the refrigerants used in those times were discarded now. Why? Because they are no longer in use. No longer in use. Actually, NH3 and CO2 are slightly used in these days too, but either sulfur dioxide, and methyl chloride and all are no longer in use because of their lack in thermal stability. Lack of Why? Because of because a lack of chemical and thermal stability of chemical and thermal stability. So these compounds are not chemically or thermally stable for use. So these compounds are no longer in use. They are discarded now. So instead of these reference, now new compounds like halocarbon compounds. So what do you mean by halocarbon compounds? Those are compounds which consist of halogens and carbon. Halocarbon, halocarbon compounds, hydrocarbon compounds, etc. are used nowadays. So the suitability of a refrigerant, the suitability of a refrigerant uh, depends upon their properties. Determines it is determined based on their properties. Very important. So there are a lot of desirable properties for a compound to be a good refrigerant. A compound to be a good refrigerant, it should have different types of desirable properties. So these properties can be of three types. So desirable properties, and these properties can be of the three to four types. Okay, first one is thermodynamic properties like boiling point, freezing point, and all. Second one is physical properties. Third one is chemical properties, and some other properties like some other miscellaneous properties. So I will explain all these properties now. So first we will move to thermodynamic properties. So a compound, a chemical compound to become a good refrigerant means it should have some desirable thermodynamic properties like first one, low boiling point. Low boiling point. So why boiling point should be low? Because the boiling point should be low because the liquid has to vaporize at the evaporator coil to cause refrigeration effect, right? So the refrigerant should vaporize in the evaporator coil to cause refrigeration effect. So the liquid at the evaporator coil should therefore vaporize easily. Easily means it should have a low boiling point. Otherwise, the compressor will have to create too much of vacuum to cause the liquid to evaporize. Okay, so that is why it should have a low boiling point. And next point is it should have low freezing point. Low freezing point. So why the freezing point should be low? The freezing temperature should be well below the operating evaporator temperature. Why? Because since the freezing temperature of most of the because if the freezing temperature of the refrigerants are not so low means it will be easily solidified, right? It will be easily frozen means it will become solid. If it has become solid means there will be choking taking place in the pipeline and or in the evaporator. Blockage will happen, right? So reference should never go to its solid state. It should always remain in either liquid state or vapor state. That is why the low freezing point of the reference should be very low. Third point is condenser pressure and evaporator pressure. Condenser pressure and evaporator pressure. So condenser pressure and evaporator pressure should be positive, means it should be little bit above atmospheric. Why? If it is not above atmospheric means If it is below atmospheric means there will be a chance of leaking the atmospheric air into the system, right? There will be a flow from atmosphere into the pipeline or into the refrigeration system. It should never happen. Okay, if it happens means it's heat transfer. The amount of heat being carried become higher. So it won't be easy for the refrigeration system to work. So it should be as the pressure should be as near to the atmospheric pressure as possible to prevent the leakage of air and moisture. Okay, if moisture is leaked into the refrigeration system means it will get clogged. It will get clogged in the pipeline and all. So too high evaporating and condenser pressure is also not desirable because it will cost the uh, compressor to become a larger in size. So too high pressure is not also desirable, too low is not also desirable. So it should be as close to the atmospheric pressure but a little bit higher than the atmospheric pressure. So don't increase the condenser pressure and evaporator pressure to very high value, because high value means the compressor size will also become larger. The pipeline will become with a higher size. So those things will increase the initial cost of the system and all. Okay. So these are the properties, basic thermodynamic properties. And one more property, critical temperature and pressure. So fourth one is critical temperature and pressure. Students, it is the critical temperature is the highest temperature of a refrigerant at which it can be condensed to a liquid regardless of the pressure, regardless of a higher pressure. So it is the maximum temperature at which it can be a vapor can be the refrigerant vapor can be condensed to a liquid. So it should be the value of that temperature should be above the highest condensing temperature that can be. So it should be above the condensation pressure, condenser pressure. Okay, it should be above the condenser pressure. So once the refrigerant is compressed, the temperature of cooling water should be, the cooling water means the water, the fluid that is flowing through the condenser which extracts the heat. So the temperature of the cooling water should be low enough, below the critical temperature of the refrigerant, to be able to condense these vapors to liquid form. Okay. So if the critical temperature of a refrigerant is too near to the desired condensing temperature, it means power consumption increases. So these are the thermodynamic properties that should be taken care while selecting a refrigerant. Now we will move to physical properties. Physical. Physical properties means it should have a low specific volume of vapor. Low specific volume. Low specific volume of vapor. Vapor specific volume should be low means why specific volume of vapor should be low? So vapor produced after evaporation of the liquid at the evaporator coil should occupy minimum volume. Why? To keep pipeline diameter, compressor size, etc. as small and compact. So if the specific volume of the vapor is high means the size of compressor increases, because the size of compressor depends on the volume of suction vapor per tonnage of refrigeration. So it should be kept low. And the next point is low specific heat. So the specific heat of the refrigerant should be low, otherwise there will be a large sensible heating or cooling taking place in that refrigerant. And the latent heat of vaporization should be high, right? High latent heat of vaporization. High high latent heat of vaporization. Because it should absorb maximum possible heat energy with the minimum amount of refrigerants. So latent heat of vaporization should be high, right? Then only we can achieve more tonnage of refrigeration. And the next point should be it should have low viscosity. Low viscosity. Low viscosity because it should be able to flow freely. Otherwise the power consumption by the compressor will be higher. It should apply more work to make the fluid to travel around the cycle. Okay, and it should have high dielectric strength or insulation, conductivity or what, high electric insulation. So it should not conduct electricity but high thermal conductivity. Thermal conductivity should be high, electrical conductivity should be low. That is, electric insulation should be high. Okay, these are the physical properties, and now we will move to chemical properties. Chemical properties means it should be non-toxic, right? Because in refrigerants and all we will be using food items to get refrigerated. If there is a leakage of refrigerant means if it is toxic means this food will get affected. So almost all the time the refrigerant we are using in any type of refrigerating system should be non-toxic. Okay, non-flammable. It should not get uh, explosive or flammable, right? Non-explosive. Chemical stability, it should be chemically stable, right? No, non-irritating, it should be non-irritating. It should not cause any harm to human, or it should be odorless. It should not have any odor. Okay, these are the desirable chemical properties, and there will be some other properties or miscellaneous properties, other properties apart from thermodynamic, physical, and chemical properties. Other properties include it should be ease of handling, easily available, ease of availability, cost. It should have low cost, right? It should it should be easy to identify the leakage. Ease of leakage location. So if the refrigerant is leaked means it should be able to get located easily, otherwise it will harm the system. Okay, if the refrigerant is getting leaked and it is not able to find that leakage easily means the system fails, right? System fails. So these things, and it should be able to produce high cop means with very less amount of work we should be able to produce large amount of refrigeration. So there is high coefficient of performance, low pressure, low power consumption per tonnage of refrigeration, low pressure ratio and pressure difference. All this comes under this miscellaneous properties. So you may be asked in exams to write the desirable properties required for a compound, a particular compound to be a good refrigerant. then you have to mention all these different properties, and should be classified separately as thermodynamic properties, physical properties, chemical properties, and miscellaneous properties. Okay, so this much properties and their explanations are required when such a question is asked. So these questions are repeated in every university examinations. What are the desirable properties of a refrigerant? So mind you, you should learn all these properties thoroughly, and chances of asking these questions is very high. Okay, students, now I will show you. I will tell you about the classification of refrigerants. So basically, refrigerants are classified into two. First one is primary refrigerant, second one is secondary refrigerant. So what is primary refrigerant? Primary refrigerant means those refrigerants which are direct, which takes part in the which flows direct which takes part directly in the refrigeration system. The refrigerant which directly take part in the refrigeration system and is allowed to flow freely in the refrigerating machine. So students, if this is a refrigerating system, evaporator, expander, compressor, condenser, that fluid which actively takes part in a refrigeration system, which flows directly inside, which directly take part in the refrigeration system, is known as primary refrigerant. So it flows directly through this refrigerating system. It undergoes a cyclic process in this refrigerating system. But what is secondary refrigerant? Secondary refrigerants are those refrigerants which does not directly take part in this cyclic process inside the refrigeration system. But what happens is that, suppose this evaporator is not directly in contact with the space to be refrigerated, but suppose this is our space to be refrigerated, a secondary refrigerant will flow through this space to be evaporator, and this secondary evaporator now flows through the secondary refrigerant flows through the evaporator and get recycled. So here an heat exchange takes place between secondary refrigerant and primary refrigerant. This secondary refrigerant transfers heat to the primary refrigerant. So secondary refrigerant is used to flow through the space to be evaporated and absorbs the heat from the space to be evaporated and carries it to the evaporator, and then rejects this heat to the primary refrigerant in that evaporator, and again moves to the space to be evaporated. So that is the function of a secondary refrigerant. So here secondary, here primary. So secondary refrigerant does not directly take part in the refrigeration process taking place in that refrigeration machine. Okay, it is just a medium. It is used as just a medium for absorbing the heat from the space to be evaporated and then carrying it to the VCR system, and then rejecting this heat to the primary refrigerant. So in air conditioning and all, air can be termed as a secondary refrigerant. Why? Because in air conditioning system, air is absorbing the heat from the room and all, and this absorbed heat is carried by the air to the refrigerating system or air conditioning system, where it rejects this heat to the evaporating coil, and through the evaporating coil some refrigerants may be flowing, primary refrigerants. These primary refrigerants absorbs heat from the air, and the process continues. Okay, so air, water, and brine, all these things can be considered as secondary refrigerants. So students, Examples for primary refrigerants are basic refrigerating compounds. So they can be of different types. Okay, in the initial period, halogen hydro initial period halocarbon compounds. I said halocarbon compounds means CFCs, chlorofluorocarbons were used, but these chlorofluorocarbons are like R11 or CCl3F means trichlorofluorocarbon. So this is termed as R11. Refracting is the term nomenclature for this CCl3F. CCl3F is R11, and CCl2F2. This is difluorocarbon. Not carbon. This is methane, right? Okay. So this is trichloro trichloro monofluoromethane. This is difluoromethane. Why? Because this is methane means this is actually CH4 compound. CH4 compound where H is replaced by three chlorine atoms and one fluorine atom here, two chlorine atom and two fluorine atom here. So basically it is a methane. It is a derivative of methane. So that is why these compounds are called as trichloro monofluoromethane and difluoromethane. So R11 and this is R12. Okay, and there are compound called C mono bromo trifluoromethane and R30. Mono C BRF3 is the monobromo trifluoromethane. So this is R30. Okay. So such kind of CFCs are the basic what basic halocarbon compounds used as refrigerant. But students, due to the presence of Cl3 here, actually this CFCs has got very high desirable properties that like we have mentioned in the mentioned just now. It have very low boiling point, freezing point, and low viscosity, high thermally stable, chemically stable. They have got high critical pressure, critical temperature. Okay, so this they have got very so much amount of so many desirable properties are there, but there is a undesirable property, mainly due to the presence of chlorine. Its ozone depletion potential. ODP means ozone depletion potential. Ozone depletion potential is high. Ozone depletion potential is high. So in order to reduce this, in order to counter this problem, later on these CFCs were started to get substituted by those compounds which have chlorine atoms very less in amount. So in order to reduce the chlorine atoms, we have to substitute this chlorine with hydrogen. So later on, instead of CFCs, HFCs started to get used. HFCs means hydrogen fluorocarbon compounds. So chlorofluorocarbons and fluorocarbons with the hydrogen instead of chlorine. The number of hydrogen atoms started getting higher in number. So HFCs started to be used by reducing the number of chlorine atoms. Okay, so R22 and all. R22 is termed is nothing but CHClF2. CHClF2. Here chlorine atom one comparing with this compound, comparing with R12, one chlorine atom is substituted with one hydrogen atom. So this is monochloro difluoromethane. So here one chlorine atom is substituted with a hydrogen atom. So we were able to reduce the number of chlorine atom. So ozone depletion potential is reduced a bit. Okay. So R22 is used, but still there is a chlorine atom. So in order to reduce this chlorine atom, in order to remove this chlorine atom, some compounds like C2F3, sorry, in order to reduce this, in order to remove this chlorine, R30 is nothing but methyl chloride, CH2, Cl, not this one, this is still chloride, R134, R134. R134 is used. R134 is nothing but tetrafluoroethane in CF3CH2F. CH3CH2F is tetrafluoromethane, tetrafluoroethane, because it has two carbon compounds. So it is ethane. Tetrafluoroethane is here. Actually, there is no chlorine atom. So we were able to reduce the ozone depletion potential to a very low value, due to the absence of chlorine atom. Still there is fluorine atom. Even though chlorine atom is reduced, means still the presence of fluorine has got a disadvantage of global warming potential. Global warming potential. So you know the greenhouse effects and global warming and all. The global warming potential of this mainly HFCs, hydrogen fluorine carbon compounds, is even higher. So this in order to reduce this global warming potential, instead of HFCs, directly HCs started to be used. HCs means, what are HCs? These are hydrocarbons. Hydrocarbons started to be used. Hydrocarbons means the compound consisting of carbon and hydrogen only. It may be unsaturated or saturated, right? So unsaturated and saturated compounds are there. But the problem of carbons is that it has got plenty of hydrogen atoms in it. Presence of hydrogen. If presence of hydrogen means inflammability, it will be highly flammable. The compound will be highly flammable. So there are a lot of things we have to take care of. Presence of hydrogen will increase the flammability. Presence of chlorine will increase the ozone depletion potential. Presence of fluorine, chlorine, and hydrogen together, carbon together, increases the global warming potential. So all these things are there. There is no concept. There is no ideal fluid. There is no ideal refrigerant. Every refrigerant has got its own disadvantages and advantages. So not possible. Ideal refrigerant is not possible. So we select a refrigerant based on our requirement. So we try to select a refrigerant based on our requirement, which has got a low global warming potential, low ozone depletion potential, low flammability, and low boiling point, low freezing point. All these properties should be taken care, and reference should be selected accordingly. Okay. There is another type of refrigerant called azeotropes. Azeotrope refrigerant. So azeotrope refrigerant is nothing but a stable mixture. A stable mixture of refrigerants whose vapor and liquid phases retain identical compositions over a wide range of temperature. So those refrigerants whose vapor and liquid phases can retain their identical compositions even at a wider range of temperature. So such a stable mixture of refrigerants are called azeotrope. Why we are mixing two different refrigerants? Because there may be some refrigerant which has got a low ozone depletion potential and global warming potential. There may be another set of refrigerants which have got good thermodynamic and physical properties. So in order to incorporate these advantages of different refrigerants together to get a more stable mixture which has got the advantages of all the different refrigerants, so that will be good, no? That will be a nice thing to do, so that we can get all the different advantage desirable properties together in a mixture. Okay, so such a mixture is called azeotrope. Okay, so example from azeotropes are, so R500. This azeotropes has got it is based on the numbers will be higher than 500. Basically, they are 500 series. So R500 is a mixture of R12, R 78 percentage of R12 and 26. Sorry, okay, 70. This should be 73.8 percentage of R12 and 26.2 percentage of R152. So such a mixture is known as R500 and azeotrope, and there is another azeotrope known as R502. It consists of 48 percentage of R22 and R22 and 51.2 percentage of R115. Okay. So you may be wondering, what is this R115? What actually is that a reference? What actually is R22? What actually is R12? So in order to understand this term, you should know how to name a reference based on the nomenclature widely accepted by the ASHRAE body and all. There are a lot of bodies, international bodies for this naming, the theories of the for refresh purpose. ASHRAE is the body that governs the laws, the things for refrigeration. So we will discuss now the nomenclature of a refrigerant. Nomenclature of a refrigerant. Suppose we have a compound. We have a compound of CFC, HCFC. HCFC means it has got all atoms of hydrogen, chlorine, fluorine, carbon, HCFCs. Okay, suppose the compound is like C has got m number of atoms, H has got n number of atoms, fluorine has got p number of atoms, and chlorine has got q number of atoms. So the refrigerant nomenclature, the name of this refrigerant is written like, it should be, this refrigerant is designated like, so CM HNFPClQ, right? So it should be designated with R in the front. Okay, it should always start with R. So this is, it should start with R and a hyphen. Okay, and the first number should be like m minus 1. So if there is m number of carbon atoms, the first number should be m minus 1. Second number should be n plus 1, and third number should be directly p itself. So R will be followed by 3 digits. The first digit should be m minus 1, second digit should be n plus 1, and third digit should be p. Okay, so you may know, the relationship between m and m, n and p, right? If this is an unsaturated, if this is a saturated compound, okay, sorry, if this is unsaturated compound means n plus p plus q. N plus p plus q should be how much? 2m plus 2, right? So for unsaturated compound, methane, ethane and all, how to calculate the number of other atoms, the common covalent bond and all, you know, right? So n plus p plus q should be equal to 2m plus 2 for unsaturated compound. Right? So suppose you have CCl2F2 difluoromethane. How to write the designation for this particular refrigerant? You write R first, okay, and it should be m minus 1, n plus 1 and p, right? So here m is equal to 1, n is equal to 0, right? And there is no hydrogen. P is equal to 2, Q is also equal to 2. So R m minus 1 means 1 minus 1 0, n plus 1 is 0 plus 1 1, P is 2. So R012 can be written as R12 itself. So the name for this difluoromethane is R12. So this is unsaturated compound, right? And so in the case of one more example I will tell you, dichlorotrifluoroether. So can you write dichlorotrifluoroether? So what is dichlorotrifluoroether? Dichloro trifluoroethane. So ethane is an unsaturated compound. So chlorine is Q equal to 2. Fluorine is tri. Tri means P equal to 3. Ethane means carbon. Carbon compound M equal to 2. Right? P equal to 2. Sorry. P equal to 3. Q equal to 2. M equal to, how much is the M? M is 2. And what will be the amount of H? H means N. How much N? N plus P plus Q should be 2M plus 2, right? So 2 plus 3 plus N should be 6. So N will be 1, right? So hydrogen should be 1. So what will be the refrigerant designation? R. M minus 1 means 2 minus 1 1, n plus 1 is 2, and p is 3. So R123. So dichlorotrifluoroethane is R123. So this is how we designate a refrigerant. So this is for unsaturated compound. In case of saturated compound, same method persists, but the difference is n plus p plus q. N plus p plus q should be equal to 2m. Right? N plus p plus q should be equal to 2m in case of ethene, propene, butene and all, right? Unsaturated compounds. So this change remains. And in case of inorganic compounds like ammonia and all, so inorganic compounds like inorganic compounds means compounds which don't have carbon. So like NH3 and CO2 is also considered as an inorganic compound, and water. Inorganic compounds mean and these for designation of these inorganic compounds, these are uh, it should be like R700 plus molecular weight of this of the compound. So for NH3 the molecular weight is 17, so it should be R717. CO2 it should be the molecular weight is 44, R744. H2 the molecular weight is 18, it should be R718, R780. So it should be 700 plus molecular weight. This is how we designate an inorganic compound. Okay, so this is a method of nomenclature of these various refrigerants. Okay, various refrigerants. So students, I think I have explained the basic things about refrigerants, and as a part of an assignment, you can read much about the various properties of different refrigerants used in the current industry, or not only in the current scenario, the earlier scenario also you can read what are the various properties of different refrigerants. You try to read. So in a textbook of Kurmi and all those things are given in a broad manner. Okay, so try to read all those properties. Try to find the various boiling points of different refrigerants, their freezing point, their condensing, their critical pressures. Okay, all these things, their ozone depletion potential or their global warming potential. Try to understand all those values data and compare those data with each other. So how one refrigerant remains prominent over the other, or why some of the references are desired more than others. So all those things, try to understand yourself. Try to read a lot about this refrigerant. Okay, so with this I will conclude this session. Thank you.